Good day, Miss Michelle Pangandoyon. I am Miss Mante, 40 years old, currently affiliated to DepEd Surigao City, particularly the Surigao City National High School as Teacher 1. Now, here are some problems in topology with the respective solutions for my completion exam. Here are first question, number 2. Let R be the relation in the positive integer natural numbers defined by R is the set of quantity x and y such that x and y is element of natural numbers and x plus 2y is equal to 12. First, write R as a set of ordered pairs. Second, find domain of R, range of R, and inverse of R, or R raised to negative 1. Third, find domain R in relation to the range R and domain R in relation to inverse R, or R in raised to negative 1. So here is the solution. First question for write R as a set of ordered pairs. R is equal to the set of quantity 2 and 5, 3 and 3, quantity 4 and 8, and quantity 12 and 0. For the second answer, or the second solution, domain R is equal to the set of 2, 3, 4, 12, and range R is element of the quantity 5, 3, 8, 0. While range R, or then in range of inverse R, or R in raised to negative 1 is equal to the element of quantity 2, 3, 4, and 12. For the third one, R in the domain R in relation to the range R is equal to the quantity, or the element of the quantity 2 and 5, 3 and 3, 4 and 8, 12 and 0. Next, number 3. Prove that B quantity A is equal to not set if and only if A is both open and closed. So our proof, let B quantity A is equal to null set. Then A complement of A is equal to A minus B of A, and complement of A is equal to A minus the null set. Therefore, A complement is equal to A, which is A is open. A prime, another proof is A prime is equal to A union of B and B of A, and A prime is equal to A union of null set. Therefore, A or prime A is equal to A, then which is A is closed. Thus, A is open since A is both open and closed. Therefore, complement of A and A prime, complement of A is equal to complement is A prime. And if we substitute then A and complement of A minus D B of A is equal to A the union of B and union of B of A. So this is the only possible when B of A is equal to null set. So number 6, prove if A prime is equal to null set, then A is closed. So our solution, we need to show that X minus A is open. Example, or IA, complement of A is open. So let X element of X minus A, and right to the right solution, it's X is not element of A, given that the set of A prime of limit points of A is empty. Hence, it is not a limit of A. Therefore, there is a neighborhood X of X such that the neighborhood of X is intersect the A equals to null set. By definition, every neighborhood of a limit point of A intersects A. So the right solution is neighborhood of x is less than or equal to x minus a. Hence, for each x is element of x minus a, there exists an open set ux, or the neighborhood of x, such that x is element of neighborhood x is close or open, rather is open to x minus a. And in for right definition, right solution is x minus a is equal to the neighborhood of x in union of x such that x is the element of x minus a. So a union of open sets, hence x minus a is open. Next, number 7. Consider a discrete topology D on x is equal to the element of A, B, C, D, and E rather. Find a subbase of the sigma or the summation for D which does not contain any singleton sets. So our solutions now, if we consider the collection of all non-singleton sets of x, it will definitely form a subbase of x. However, if we need smaller subbase, we can just consider sigma or summation is equal to the set of ABC, set of ADE, set of BD, set of CE. Note that in a singleton A or a singleton of A set is equal to, singleton of A rather, is equal to element of A, B, and C is intersect with A, D, and E. And singleton of B is equal to the sets of A, B, C intersect with set B, D. Singleton of C is equal to the element of A, B, and C intersect with elements of C and E. Singleton of D is equal to A, B, set of A, D, E intersect with set of B and D, B, D rather. Then singleton of E is equal to A, B, element of A, D, E intersect with element C, A, E rather. Since singleton form a base for discrete topology, the collection of all finite intersections of sets in sigma or in summation form a base for D. Therefore, sigma or summation forms a subbase for D which does not contain any singleton set. Another number. Prove or disprove the absolute value function f on real numbers. That is f of x is absolute of x, for x is element of real number is continuous. So our solution, our answer for number 15, let the summation is greater than 0 and C is element of real numbers. So take the delta is equal to the summation or the sigma, then for all x is element of real numbers where absolute of x minus C is less than the epsilon. So the absolute of f of x minus f of C is equal to the absolute value of x, absolute of x minus the absolute of C is less than or equal to the absolute of x minus C is less than to sigma delta, or the epsilon is equal to delta. Note, to prove, use epsilon delta definition. So a function of f d to the right is a real numbers is continuous at a point of C element of D if for all E or summation or the sigma is equal, is greater of 0, there exists sum of delta is greater than 0 such that for all x is element of D where absolute of x minus c is less than by delta, we have f of x, absolute of f of x minus f of c is less than the epsilon. Our last number, number 18, let x is equal to natural numbers with topology t is equal to g such that g is open to natural numbers or subset of natural numbers, where x is element of g. Left and right solution, every divisor of x is in g. Find and a where a is equal to 1, 2, 3 or sets of 1, 2, 3, 4, 5. So our open solution, our open set solution, open topology solution, let x is element of int a or internal a is in the for the right solution, there exists a neighborhood g of x such that g is a subset of a. In right solution, where x is element of g is open, and the right solution also x is element of the union of g such that g is open and g is subset of a. In closed solution or in closed topology, let x is element of union of g such that g is open and g is subset of a. For right solution, x is element of g such that g is open and g is subset of a. For some, g is element of the union of the singleton g or element of g. Right solution, x is element of g less than or g is a subset of a rather, and in the right solution where x is element of int a. Therefore, the int a is equal to union of g such that g is open, and that's all. Thank you.